No, Mel hates that noise. Aw. Hello, in this video we're going to be talking about concavity. And what concavity has to do with is derivative stuff, particularly the second derivative. If we looked at this, we know stuff about the first derivative. We know that the first derivative is going to have values of 0 at these maximum and minimum values. And then we're going to get negative first derivatives whenever this thing is decreasing. And then we get positive first derivatives whenever this thing is increasing. If we start looking at the second derivative, it can't talk about that increasing and decreasing thing because that's what we talked about with first derivative. We care about like how it is increasing, or if you think about um, velocity versus acceleration. What it translates into is this idea of these U shapes. So, like right here in this region, we kind of have this concave down shape. While over here in this region, we kind of have like this kind of upper U thing. Same thing over here. We kind of have like this upper U thing. And then in the middle, we've got that going down U thing. Here's what I just said, but in words that are typed on the screen. We are concave up when our second derivative is positive and concave down when our second derivative is negative. Now remember, this does not have to do in terms of increasing and decreasing. Here we are concave up and increasing because our first derivative is positive. Here we're also concave up, but our first derivative is negative, so we're decreasing and concave up. In this spot right here, we're kind of making this kind of like downward shape U. So these are concave down. However, this first one is increasing and the second one is decreasing. So increasing and decreasing are not connected to concavity. They are separate ideas. I don't know what Finney's on about with this concavity test. Really, they're just asking us figure out where it's concave up and concave down. So we need to take a look at our second derivative to determine that. So we go y prime equals negative 4x cubed plus 12x squared minus 4. That is our first derivative, but in order to determine concavity, we need to look at our second derivative. So that's going to be negative 12x squared plus 24x. Now, to determine where we're going to be concave up and concave down, we need to see when this thing shifts signs, when it shifts from positive to negative. So it's probably going to do that right around where it equals 0. So I want to kind of know, when does this second derivative equal 0? So I can factor out, I'm going to factor out a negative 12x from both of these. So then I get x minus 2 equals 0. So the two places that this thing equals 0, the second derivative equals 0, is when x equals 0 and when x equals 2. Now I want to make a sign chart in order to be able to determine what is going on in terms of positive and negative spots. So it's going to be at the two values that I found, and I want to see if it's changing signs on either side of those. So if I plug in some value like negative 1 into my second derivative right here, I would get negative 12 minus 24. So that's definitely going to be negative. So on this interval, we're going to have a negative second derivative, meaning we are going to be concave down. Then we check something between 0 and 2. So 1, if we put a 1 here, we would get negative 12 plus 24. That's going to be a positive value. So we're going to get a positive value here. So we're going to be concave up. Finally, we check some number that's bigger than 2. I'm going to do like 10. So we get negative 1200 plus 240. That's not going to be very close. So that's definitely going to be a negative value. So this is also concave down. So we've got two intervals where we're concave down and one interval where we're concave up. So now we just got to write that out. So y is concave up on the interval of 0 to 2. Note that I'm not including 0 nor 2 because it's not positive there. It's 0. It's not positive nor negative, so it's not concave up nor concave down. And then y is concave down on the intervals of negative infinity to 0 and 2 to infinity. Note here in my writing, I'm actually writing out the word concave down. I did use CCD up here when I'm just kind of like doing my scratch work, and that's okay. But when you're actually writing out your answer, please spell out concave up and concave down, just so that they don't kind of come after you for like weird things. In this next example, again, we're looking for where it's concave up or concave down. I've taken the liberty of just like finding those two derivatives because they're kind of long to find out, and I mostly want to be talking about this concavity thing and not quotient rule. So I just found those two derivatives, and I need to see when this thing is going to equal 0. So I just take that numerator and set that equal to 0. So negative 36x squared plus 4 equals 0. So that is going to be x squared equals, let's see, negative 4 divided by negative 36. That's going to be 1/9. So that's going to be when x equals plus or minus 1/3 are two places where this thing could equal 0. Now, I do want to check one more thing because we could get something weird when this denominator equals 0, because then our second derivative won't work. And we might have that shift from positive to negative from that denominator. So again, I want to set that equal to 0. So 3x squared plus 1 equals 0. When I go to solve that, I get x squared equals negative 1/3. And then I'm like, uh-oh, because when I square root, I get plus or minus I over the square root of 3. And that's an imaginary number. So there's no real numbers that I could put in here that's going to cause that denominator to be 0. So I don't have to worry about the denominator. I only have to worry about that numerator equaling 0. So let's make a number line just like we did in the previous one. I am glad that I checked that denominator because it could have equaled 0 and then I would have had to add those numbers onto here. But since I over the square root of 3 doesn't exist on the real number line, don't have to worry about it. Okay, now these are gross, but hey, I can test with normal numbers. So I'm going to test with 0. So if I put 0 into here, I get a positive 4. And then in the denominator, I'm going to get, well, this will all be positive. So a 4 over some positive value, that is going to be a positive thing. So in between negative 1/3 and positive 1/3, we're going to be positive second derivative. So we're going to be concave up. Almost wrote concave down. If I check some number that's bigger than 1/3, so I'm going to check like a million. So then this will be really, really huge if I plug in a million into that. Plus 4, that's still really big. But it'll be negative. It'll be a really big negative number. And then this will be a real big positive number in the denominator. So a negative divided by a positive. Oh, that is going to be definitely negative. And it will be concave down. If I do that same thing with like negative a billion, it's going to work out to be the same thing. That negative will get squared and become positive. So overall, this is a really huge negative number. And then in the denominator, it'll square and become positive. And so this denominator will be a really big positive number. So we got negative divided by a positive. That is going to be negative. So this will also be negative, and we're concave down. So we've got our intervals. Now it's just a matter of writing that up into sentences. So f of x is concave up on the interval of negative 1/3 to 1/3, and we're concave down on that interval of negative infinity to 1/3 and 1/3 to infinity. I'm choosing to use interval notation to talk about the intervals of concavity. You can use inequalities too. That's fine. It's up to you. But do note that I am still spelling out concave up and concave down. Another example here dealing with this concavity. Again, I've just kind of zipped through the derivative stuff. I broke it up into several fractions, then found the derivative of each one of those fractions, so I wouldn't have to quotient rule so much. And then did the derivative twice, and then I put it back together to make this final fraction. In order to figure out where the graph is concave up and concave down, again, I care about when is that numerator going to end up equaling 0. So I got a little solving to do. So negative 2x cubed plus 8x equals 0. Let's see, we could factor out negative 2x. So then we have x squared minus 4 equals 0. And ooh, that could factor again. So negative 2x, we got an x plus 2 and an x minus 2. So those are two places where we could potentially be shifting from being positive and negative in our second derivative. So let's make a sign table. And then we just got to check each one of these to see if we're changing signs on these intervals. So if we do something like negative a billion over here, then this overall is going to be a positive value, very, very large positive value. And then this will be a negative value, but it won't be as big. So overall, that thing is going to be positive because then we're being divided by 9. So we'll be positive right here, meaning that we're going to be concave up. If we test negative 1, I think that's going to be our best option. Then let's see, this is going to be a positive 2. Yeah, positive 2 minus 8, that'll be negative, and then divided by that positive 9, that overall is going to be a negative value. What exactly it is, I don't really care. I just care that it's definitely negative. If I put a positive 1 in, then this will be a negative 2. And then plus 8, that'll be like positive 6 divided by 9. Okay, overall, that thing is going to be positive. So that's going to be concave up. If we check our final interval, if I put in some huge positive number, then this will be some huge negative number. This will be a positive number, but it won't be as negative. So overall, that thing is going to be negative up top there. So then we're going to be negative on this interval, which means we'll be concave down. Now all we got to do is just write a sentence. So y is concave up on the intervals of negative infinity to negative 2 and 0 to 2, and y is concave down on the intervals of negative 2 to 0 and then 2 to infinity. As soon as we check that one number on each one of these intervals, then everything is going to be working out. So we've been doing all this talk about like when that second derivative equals 0, and that's a lot to say. So we want a fancy name for it, and the fancy name for it is that point of inflection. The point of inflection is where our function shifts from being either concave up to concave down, or being concave down to being concave up. So in this example here, I've got inverse tangent, and I found its second derivative. I checked when that thing was going to be equaling 0. I just had to worry about that numerator. There isn't a way for that denominator to equal 0. I would be the only thing, but that wouldn't show up on my number line. Then if we check either side of it, we get concave up on one side, concave down on the other side. So we do get a point of inflection here. And since they are talking about a point of inflection, I want that coordinate point. It's not the value of inflection, it's the point of inflection. So I want to figure out where that coordinate point is. So I took the 0 that I got here and plugged it back into the original function so I could get that coordinate point. So we wrap this up by saying there's a point of inflection at 0, 0, since the graph on the graph of y, since y double prime changes from positive to negative at that point. Let's put that all together and figure out what's going on with the concavity and find our points or points of inflection for this graph. So I need to figure out what's going to go on with the second derivative, but to do that, I first have to find the first derivative. So that's going to be negative 1 minus 12x cubed. And so then f double prime of x equals, let's see, that's going to be negative 36x squared. So when that thing is going to equal 0, that's going to tell me my potential points of inflection. We do want to be careful that they're not liars and that they actually are points of inflection. So negative 36x squared is going to equal 0 when x equals 0. So that's my potential location. I could plug that in to figure out, well, it would be 0, 4 if we plugged it back into the original. But is it actually a point of inflection? Well, we got to check by doing our cool sign chart. So we're doing 0 and we're checking what's going on with y double prime. If we put in some value that is less than 0, like a negative number, we put a negative number right here, that'll become a positive number multiplied by that negative 36. That will be negative. So we're going to be concave down right there. If we do some positive value, some number that's bigger than 0, then if we plug that positive number in here, we'll square it, we'll get a positive value multiplied by that negative 36. That's still negative. We're still concave down at that point. So 0 is not a point of inflection. We know that it has no points of inflection because we checked everywhere and it was constantly concave down, so it never shift from down to up or up to down. So then we would also say, hey, f of x is concave down on the entire interval, negative infinity to infinity, all real numbers, whatever you like. It's always concave down. And you can use that as a justification about why f of x has no points of inflection. It needs to shift from positive to negative in order to be a point of inflection. That is it for our video on concavity. So remember that concavity is separate from increasing and decreasing. Both of these curves right here are concave up. This one is increasing and concave up. This one is decreasing and concave up. Both of these are concave down, but this one's increasing and concave down, and this is decreasing and concave down. And that point of inflection is where we shift from either being concave down to concave up or being concave up to concave down. Make sure you have this diagram in your notes. It's really nice as a quick reference of like, okay, what would that precisely look like? Thanks for watching. Hope you took good notes, and I'll see you next time. Bye-bye.